Coming up on Dr. Kiki Science Hour, we're talking about the science of the sun and the Solar Dynamics Observatory. That's up next on Dr. Kiki Science Hour.
Netcasts you love.
From people you trust.
This is TWiT. Bandwidth for Dr. Kiki's Science Hour is provided by Cachefly at CACHEFLY.com.
This is Dr. Kiki Science Hour with me, Dr. Kiki. Episode number 147, recorded Thursday, June 7th, 2012. Staring at the sun. This episode of Dr. Kiki Science Hour is brought to you by Netflix. Watch thousands of TV episodes and movies on your PC, Mac, iPad, iPhone, or TV instantly. All streamed directly to you, saving you time, money, and hassle. For your free 30-day trial, go to netflix.com/twit. Welcome, everyone. This is Dr. Kiki Science Hour, and I am Dr. Kiki. I'm so glad to be joining you from suddenly a very bright location. I'm being blinded by a light. The sun is reflecting off a window outside my hotel room in New York City. So sorry about the white balance on the video at the very beginning of the show. Yeah, I'm in New York City and I'm having a great time. There's so much science in this city that, you know, it's very hard to avoid it. I trip over science in the subways. But today, it's all about talking about the sun. You guys ready to dig into this? I'm being blinded by it right now, seriously. And it is suitable because we're talking about the science of staring at the sun or looking at the sun with our guest, Todd Hoeksema, and he is with Stanford University Solar Observatories Group. But first, before we get into that, a few science headlines. It's June 7th, 2012, and this is the science that made headlines this week. June 5th saw the transit of Venus across the face of the sun. This celestial event will not happen again until the 22nd century, so consider yourself lucky if you were able to watch it. If not, there's lots of video available on the interwebs. According to two separate reports, the early universe became a little less hazy this week. The Japanese Subaru telescope spotted a faint galaxy about 12.91 billion light years away. And Arizona State University researchers using the IMAX instrument on the Magellan telescopes at the Carnegie Institution's Las Campañas Observatory in Chile found another galaxy, which they measured to be approximately 13 billion light years and closer to the beginning of everything. So these kinds of studies are really interesting to pay attention to. Oh, and NASA announced that the National Reconnaissance Office gave the space agency a couple of Hubble-sized space telescopes that it happened to have just lying around in a warehouse in upstate New York. The scopes need a little work to be functional and might be repurposed to search for dark matter. How do you weigh a dinosaur? Well, with lasers, of course. A University of Manchester researcher laser scanned the skeleton of a Giraffa titan. That's right, a Giraffa titan, a very big dinosaur, and created a virtual model of the fossil animal in order to estimate its weight, which it calculated to be 23.2 tons. The method, when used on mammal skeletons, underestimated their weights by a consistent 21%. And since dinosaurs aren't mammals, the researcher plans to test his technique more widely. A petition started by open access advocates made its way to the White House this week after collecting 25,000 signatures. The petition urges the U.S. federal government to require federally funded scientists to share their results with the public. Sounds like a great idea. As part of the trial to determine just how much BP will be fined for the environmental damages caused by the Gulf oil spill, the judge magistrate has allowed BP to subpoena emails from scientists at Woods Hole Oceanographic Institute who were involved in estimating the size of the spill back in 2010. The scientists say they have already provided BP with over 50,000 pages of documents and that the request for the private emails is, quote, an erosion of the scientific deliberative process. University of Texas researchers published a report in the Proceedings of the National Academy of Sciences concluding that groundwater depletion from current agricultural irrigation methods threatens the U.S. food supply. They propose more sustainable farming methods for the U.S. Central Valley and High Plains in order to avert likely problems in the future. The FDA approved the testing of experimental chemotherapy drugs on early-stage breast cancer patients with aggressive forms of breast cancer. Previously, only late-stage patients were approved for such studies. Under the new guidelines, women with aggressive triple-negative breast cancers in the early stages will be eligible. Scientists at the University of Bonn published a study in the Proceedings of the National Academy of Sciences detailing their successful attempts at splitting an atom with quantum mechanics. Using lasers to hold and cool cesium atoms, the team used the laws of quantum mechanics to divide a single atom in two and hold it in two places more than 10 microns apart before putting it back together again. The precision process involved absolutely no nuclear fission. Cold Spring Harbor neuroscientists released the first data set from their efforts to map the vertebrate brain's wiring system. At 500 terabytes of data, the mouse brain being mapped is no small project, but will provide a virtual microscope to the public and scientific community. It was released pre-publication at mouse.brainarchitecture.org. The world's first intercontinental solar flight was completed on Tuesday by a solar-powered plane called the Solar Impulse. The plane started in Madrid, Spain, and landed in Rabat, Morocco, after a 19-hour flight. The Space Shuttle Enterprise docked at its new home in New York City on Wednesday. Will be on permanent display at the Intrepid Sea, Air, and Space Museum. And I do have to say there is something awesome about a space shuttle on an aircraft. Too many died this week at Ray Bradbury died this week at the age of 91. May he live on eternally in the minds of many through his words. And that does it for the science headlines this week. Let me know what you think about these science news stories, or tell me what you think should be news by emailing Dr. Kiki at drkiki.tv, or you can leave me a voicemail at 650-741-5454. I'd like to take this opportunity to thank Netflix for sponsoring this episode of Dr. Kiki Science Hour. Netflix streams thousands of TV episodes and movies directly to you instantly, which saves you a lot of money, time, and hassle. Great. 3 great things. There are several easy ways to instantly access streaming movies and TV with Netflix. You can watch Netflix movies and TV shows on your Mac, your PC, your iPad, if you have an iPad app for Netflix. You can watch on your iPhone and some Android phones as well. If you're not into the computer Netflix watching thing, you can use a gaming console like an Xbox 360, PS3, or a Nintendo Wii. You can watch Netflix right on your TV. If you're not a gamer, you can even get an inexpensive and easy-to-use set-top box like the Roku box or an Apple TV. Really great ways to get into Netflix. And with Netflix, you can watch movies and TV shows instantly on any of these devices at any time you like. And you can begin watching a movie or a show on one device, stop watching at any point in the program, and pick it up exactly where you left off. Netflix keeps track of your watching for you. It's a very seamless, easy-to-use interface, which I happen to enjoy. Whichever way you choose to access Netflix, you can watch as many movies and TV shows as you want, anytime you want, and you can cancel at any time. But right now, Netflix is offering you 30 days for free. You can try Netflix today for 30 days free. Go to netflix.com/twit. That's netflix.com/twit. And be sure to use this URL when you sign up for your free 30-day trial, netflix.com/twit. We thank Netflix for their support of TWiT and Dr. Kiki Science Hour, and we hope that you enjoy watching instantly with Netflix. All right, everybody. back to the show. It's time to get into our conversation. I'd like to welcome our guest, Dr. Todd Hoeksema. He's a solar physicist. He works at Stanford University with the Solar Observatories group and on NASA's Solar Dynamics Observatory. He's been studying the sun for years and years. And Todd, thank you so much for joining us today.
Glad to be here. It's kind of a treat.
It's a treat for me. I've been really looking forward to talking about the Solar Dynamics Observatory. Before Solar Dynamics Observatory, we had SOHO. We have these orbiting satellites looking at the sun. And once upon a time, it just used to be telescopes. And we from so far away as we are here on our planet. And now we get to be much more up close and personal with the sun. So having you on the show to be able to talk about all the things that we're getting to learn now that we're so much closer, I'm just very excited. How did you get involved in studying the sun? What was your path to where you are now?
Well, you know, when I was a kid, I was very excited about astronomy in general, and actually during college days, I'd sort of given up on it because at the time there weren't very many jobs. So when I applied to graduate school, I came to Stanford to do solid-state physics. Probably would have been a little more lucrative, but I got a call for a summer job saying, hey, would you like to work on solar physics this summer and live in an observatory? Well, who could turn that down? And it turns out it was really interesting. I love the fact that the sun is a star that actually affects people's lives. And so you can sort of combine that love of the sort of big, out there kinds of things that we see in nighttime astronomy, but also something that's a little bit practical. And so that combination of space weather, we didn't call it that at the time, but space weather and what we can do now has been really interesting to me.
Oh, I think it's got to be just fascinating. When did you get involved with the Solar Dynamics?
So SDO.
Oh, Skype.
Well, I'm going to insert your question is when did we get started with this? This is my second try or my second experience with a NASA mission. The first one was SOHO, which we started in 1986, I think it was, and it launched about 10 years later in 1995. SDO started as something in the back of our minds about 2 years after we launched, so back in about 2000, and it took about 4 years to get the whole project started and then another few to get it launched, and I was in on it from the beginning. I was actually working at NASA headquarters at the time that we were defining what the mission ought to do. And we realized that the sun was a very dynamic place, hence the name Solar Dynamics Observatory. And what we really wanted to do was be able to put together what we were learning about the inside of the sun with what we could observe about the outside of the sun's atmosphere. And so the three major instruments, or the three only instruments on SDO, look at the solar interior, the solar surface, and then the atmosphere above it.
What kind of instruments are necessary to be able to get at what's going on inside the sun versus what's outside?
Well, to look at the inside, we use a technique called helioseismology. So seismology, just like people look at what happens inside the Earth from what happens with earthquakes by sensing the waves that are propagating after the earthquake happens. You can tell what the structure is inside the Earth. The sun is actually quite similar. There are constant earthquakes, but there are constant excitations of sound waves on the surface of the sun, and they actually bounce around inside. And so the whole sun is resonating like a big bell. And from the pitch or from the frequency of those sound waves, you can tell what's happening inside. And there are different sound waves go to different parts of the interior. And as a result, you can tell whether it's rotating fast or slow. You can tell whether it's hot or cold. You can tell what it's made out of. So you can see things about the inside of a star that there's no other way to see. Because, of course, all of the light comes from a very thin region at the surface that we call the photosphere. The way we measure that is by looking at the effect of the sound waves when they bounce off the surface.
Just a ball of... Yeah, I was just asking, we think of the sun as a ball of just, we think of it for light and heat, but we don't really think of it usually as something that you would listen to.
Yeah. And, you can't listen to it directly because between the Earth and the sun, there's just empty space, and so sound waves don't propagate. But just like when a speaker, I don't know if you've ever looked at a speaker when you hit it or when it's making noise, you can see the speaker's surface moving in and out, and that's the reflection of the sound waves that you can see on the surface of the sun. So the sun surface moves in and out just like the surface of a speaker would when you can tell what the music is. So what we try and do is we try to listen to that internal music of what's going on inside the sun. You've probably
what
been,
kind of stuff?
You've probably been in
ahead.
a car when there's a one of those loud cars that boom, boom, boom. And if you've ever looked at your mirror, you know how your mirror kind of shakes every time? It's the same kind of thing. So the sun is shaking when those sound waves come.
And so it's like you said, just like a seismology experiment where you can figure out kind of what is shaking, where it's shaking, and maybe why?
Yeah, you can tell all those things. One of the main things that we've been looking at is how fast does the inside of the sun move in different areas. So the surface of the sun is kind of a funny place. It twists. The equator of the sun rotates around once every 27 days. The poles of the sun rotate around every 29 to 30 days, or even longer. If you look inside the sun, what happens below the surface? You wouldn't think it would be the same thing, but it's not a solid body. And one of the only ways to figure out what's happening is by using this seismology.
That's just fascinating. So how do you take the seismology and the listening to the sun and put it together with what we're learning about the other two areas of the sun? So its atmosphere and the light producing and the heat producing portions.
So what we look at the surface of the sun are the sunspots, and you just had one up on the screen there a minute ago. Sunspots have a cycle. They come every 11 years. There's a whole bunch of them, and then for a while there aren't so many. And this is an example of one of the big ones that we saw about a year ago in February of 2011. It was the first, what they call X-class flare of the solar cycle. We don't really understand the details of why the sun has a solar cycle that lasts 11 years. And it turns out, interestingly enough, it isn't exactly 11 years. It varies a little bit. And this one came after a cycle that lasted almost 14 years. So it was a very long cycle. And the current cycle is very weak. Now, what we would have liked to say is, well, we predicted that. But in fact, we were all pretty surprised. So the most modern models of how the inside of the sun predicted that the sunspot cycle that we're currently in would be a big one. And the old-fashioned ones that were just sort of based on, well, how big is the polar field 11 years before, said small, and so the average prediction was right in the middle. But it turns out it's small.
So this solar cycle, if you were to, right now, everyone was worried about the solar flares that would knock out our energy grid, and there are all these predictions that go in line with the 2012 end of the world stuff. It's really not living up to all the hype at this point?
Well, 2012, end of the world now, definitely not that. But, you can have a big flare in what is otherwise sort of an ordinary sunspot cycle. So there won't be the number of flares, but you could still have a really big one. And that's, again, one of the things that we don't really understand is what causes the biggest storms? Why is this active region or this sunspot region going to be bigger or more active than another one? And so we need to try and put that together. And that's one of the things that we're really trying to learn with the Solar Dynamics Observatory. We can look below the surface of the sun, and we can see what's happening underneath this sunspot and maybe compare it with what's happening under a sunspot that isn't so active, and eventually try and get at why.
That's interesting. So do we know anything about sunspots? I know sunspots are when we're looking at them, they're the dark spots on the surface of the sun from where we stand. But what do they do? What are they interacting with?
So we do know a little bit about sunspots. We know that they're about 1,500 degrees cooler than the rest of the surface of the sun. We know that they're places where the sun's magnetic field is very strong. In fact, it's the magnetic field that's really driving the fact that they're there at all. Sunspots and magnetic field regions occur on a variety of scales from small to large, and the largest ones become sunspots. They become dark. So this is a picture of it's actually a vector magnetic field. So you can see little arrows pointing out in different places. And you can now watch, as we zoom in, you can watch how it evolves over time. You'll see that new flux emerges and spreads out, and then parts of the magnetic field move past others. And if you've ever played with a magnet, you probably know that you have to store a lot of energy to move one magnetic field of one polarity, which is blue, and the other polarity red. When you move those by each other, you're going to store a lot of energy. And so what happens is the energy gets stored in the atmosphere overlying these regions, and that's what causes these big solar flares. But we don't really understand yet what causes one region to come up and be fairly mundane and another one to be a huge active region that produces some sort of killer, well, I shouldn't use such inflammatory language, but it's a big sunspot or a big solar flare.
But big solar flares pointed directly at us could really affect the planet.
Yeah, they really do. There's a lot of things that they affect. One of them is power distribution, and that's probably the one that would have the most lasting effects on us here on Earth. There have been big storms in the past where if the current power grids were there, they would be blown out. They just wouldn't be able to handle the load. And the things that get damaged are these huge transformers that are very difficult to come by and difficult to repair. And you could imagine parts of the world being without power for a long time, months to years. And you can imagine being without electricity for that long is pretty significant, would have a pretty significant impact on your economy. Back in I think it was 92, there was a big storm in South Africa, and parts of the country had to go on rationed power for months and months. And you can imagine if that happened worldwide, that there just wouldn't be the ability to make those big transformers. Power companies can do some things. If they know that there's going to be a big storm, you can do something about it. You can turn your power down, but they're not going to turn the power down if they don't know for sure that something's going to happen. So if you have a better prediction, that's another thing that we can help to prevent those kinds of events.
Yeah, being able to know exactly when there's a possibly big solar flare coming, that would be...
Yeah. I don't think we'd be allowed to get it wrong twice.
Yeah. Is it kind of, at this point, predicting earthquakes is something that we can't really do? We can predict maybe a few seconds ahead of time. Is it similar with sunspots, or is our understanding of them a little bit more advanced than what we know about our own Earth?
Well, in some ways, I think it's a little bit more advanced than that. It's more like predicting a large hurricane. And by observing the cloud systems from above and using the kind of pictures that you can take, you can tell that there's going to be a big hurricane. What you can't predict is where individual lightning strikes are going to occur, or where the tornado that's associated with the hurricane is going to land, or a month in advance, where's that hurricane going to go, and what crop should you plant the next year. And so in that sense, we can recognize now, I think, usually the active regions that are more likely to have a big flare. But we can't predict exactly when they're going to be. But it's not quite as random as earthquakes that, there's always the potential, but you don't know when it's going to happen over a much longer time period. So, yeah, a little bit better, but we still have a long ways to go.
A long way to go, yeah. For people who don't really understand the terminology for solar flares, you mentioned an X-class solar flare. What are the different classes of flares? And somebody in the chat room was also asking whether or not the sun rotates. And so can you address that question?
The biggest flares are X-class flares. And then under that are M-class flares. Under that are C-class flares. Under that, B, and then A. So you can tell that they kind of came up with kind of a funny thing. A, B, C, M, K, X. I'm not quite sure. And it really is related to factors of 10 in the energy that's associated with a flare. So an X1 flare is 10 times bigger than an M1 flare. An M1 flare is 10 times bigger than a C-class flare. And they give a number based on how many particles there are observed near the Earth. And I think the biggest flare ever was an X17 flare. So it's it's 17 times bigger than an X1 flare. So it was actually pretty. You asked about rotation.
The biggest flare that we've noticed.
The biggest flare that we've actually measured. So this one happened back in 2003. 1993, I think it was. We call it the Halloween storms because it happened around the time of Halloween. Fortunately, the big flare happened when the flare was right at the edge of the sun rather than directed right toward us, so we didn't actually experience all the effects that we otherwise would have. So you said one of your viewers asked about the sun rotating. The sun rotates about once a month, so it takes 27 days at the equator for the sun to rotate all the way around. So we get a view of something, and it crosses the disk, as we call it, in about 2 weeks. And then for 2 weeks, we don't see things. And so one of the interesting new satellites that's up is called Stereo, which is moving over toward the edges of the sun out in space, deep space. There's actually one ahead of us in Earth's orbit and one behind us in Earth's orbit by more than 90 degrees now. So we can actually see some things on the far side of the sun that we've never been able to see before. The equator of the sun rotates, like I said, at 27 days, a little bit more. But the poles of the sun rotate every 30 days or 35 days, even right at the very poles. And so that twisting motion is one of the things that we think drives the magnetic cycle that eventually leads to these sunspots.
And when you're talking about what you're observing as rotating, you're talking about the surface of the sun. Do we know whether or not similar rotation is occurring into its core?
Well, the sun is fluid, so it's like the whole thing is made out of liquid. Well, actually, it's more like it's made out of air because it's not very dense. If you were in a boat, you would float about a third of the way down before you got to something where your boat would actually float in terms of how dense it is. It's like the density of water about a third of the way into the sun, which is a long way, 200,000 miles down below the surface, 200,000 kilometers below the surface. So it's not very dense. We do know about the inside from this helioseismology. We can tell that inside we call it the outer region of the sun is called the convection zone because the material is boiling, overturning in that region in the outer one-third of the sun. Below that, we think the sun is rotating as a solid body like the Earth would, so that things aren't moving very fast. But in the outer third, this differential rotation from the surface goes down, and learning exactly the character of that is one of the things that's allowed us to make better models for the solar cycle. We think that the solar cycle is actually seated at the bottom of that convection zone, about a third of the way down. And it's there where you've got the interface between this rigidly rotating part and this differentially rotating part that really twists up the magnetic fields and causes the activity that we eventually see at the surface.
Somebody else was asking in the chat room about the thermonuclear aspect of the sun. So what's happening at the core versus the convection area? What do we know about that?
The sun has three basic regions. All of the energy is generated in the very core of the sun. It's the inner 5%. So it's bigger than Earth, but it's only 5 or 10 times bigger than the Earth. The sun as a whole is 100 times bigger than the Earth in diameter. All of the energy is generated in that nuclear burning core, where it's very hot, very dense, very thick. You wouldn't want to be there for any time at all. And then the next region out is sort of the inner 2/3 of the sun, and that's what we call the radiative zone. And it takes anywhere from 100,000 years or a little bit more for the energy that's generated in the core to reach the surface just by radiation pressure. So the electron or the photons are bouncing around in that region, but they don't actually reach the bottom of the convection zone for 100,000 years or some number like that. And then it takes about 2 weeks in this boiling region for things to get from the bottom of the convection zone all the rest of the way to the surface. And then once it gets to the surface, the light finally can escape, and it gets to us 8 minutes later.
That's amazing. So the journey... the journey is that when light finally reaches us, the journey that it's taken is millions of years, or
it's 100,000 years anyway.
100,000 years at least,
time. So if the sun were, there are other things that get out. There are neutrinos, which are little particles that are also generated in the thermonuclear reactions. They don't carry much energy, but we can detect them, and those get here immediately because they don't care about the material in between us and the center of the sun. So we would notice if the sun went out sooner. But the sun would take a while to cool off just because it has so much material between us and the very very center. And it's a good thing because we're shielded from all that high energy stuff that's going on. The surface is 6,000 degrees, but the center is 15 million degrees. So fortunately, it's a little cooler.
And we have probably, 3 billion years or so? 4 billion years or so?
Yeah, something like that.
Left our sun.
Yeah, the sun is about, I think we say about 5 billion years old, and it's probably about middle age, so about halfway through its normal lifetime. And at that point, it'll become a red giant briefly, and then it'll become a white dwarf eventually, and it'll actually live for a lot longer, a much longer time period. Recently, they discovered, or they've realized that the Andromeda galaxy is going to collide with the Milky Way galaxy, which is ours. But that'll happen before then. Now, probably we won't get hit by anything, but it'll be an interesting show. But the time scales are about the same.
Regardless, we have plenty of time to study the sun.
Yeah, we do. Maybe we'll meet
before any of these. Yeah. So the other aspect we have a movie that you've given us dealing with the brightness of the sun. What do we understand about the changing brightness of the sun and how that affects us? Is that part of this solar cycle that we're talking about?
Yeah, the term we use for it is the solar constant, but of course it isn't actually constant. And for hundreds of years, people tried to for a long time anyway, people tried to measure it from the ground. And it turns out that the atmosphere is just too noisy. You can't really measure it very well from the ground, so you had to go to space to measure it. And what we find is that the sun varies in its brightness by about 0.2% maybe over the solar cycle. So it becomes a little more active at solar maximum and a little less active, a little less bright at solar minimum. There was a time when people thought that might be a contributor to global warming, but it turns out that it's not. It's a very, very small variation, and we can look over long time periods because we can go back in the historical record and look at how much radiation was actually coming in by measuring cosmic rays and things, and we can tell that the sun actually hasn't been changing its brightness very much over reasonable time scales.
That's right. I think it's...
Lost you.
All these changes over time. Transits. Transit of Venus was this last week.
That was exciting.
Very exciting. We were able to see the planet Venus pass in front of the sun. And you mentioned earlier the sun is about 100 times larger than the Earth. The perspective of seeing Venus up against the sun, get a really wonderful perspective of how large the sun actually is.
Yeah, so Venus is about the same size as the Earth is, within a little bit. I don't know if you can bring up the movie of it crossing the sun. Some of the movies are pretty cool. But yeah, it just kind of moves on to the edge, and you're watching, and then all of a sudden you can see it, and there it is. And, twice in every 100 years, you get to see this thing move across the surface of the sun. And it's bigger than most of the sunspots, and it's really, really dark, and it was a fascinating thing. There you can see it just off the edge of the sun, off to the left, in the upper half. Yep, right up in there. And it takes about 7 hours for that to move from one limb to the other. Now, it doesn't go quite across the middle. It actually goes kind of tangent to it, but we watched it for about 7 hours the other day, and it was really fascinating to see.
So what kind of a perspective did the Solar Dynamics Observatory allow you to have? Here's another amazing image that you wouldn't have had otherwise.
That was a time-lapse view, so you were just seeing the sun, the planet move across the surface over that 7-hour period. Well, our satellite is in orbit around the Earth, 22,000 miles above New Mexico, because that's where our ground station is. So it's constantly sitting out there. So we actually saw Venus start transiting about 20 minutes later than everybody else because of the location that we happened to be in. So it was kind of an interesting thing for that reason. One of the interesting things that's going on is there's a mission called Kepler. I don't know if you've talked about that with anybody on your show or not, but
Last week.
What they're looking for is so they're looking for transits of other planets across other stars. And when you see a transit, you'd like to know what it actually means and how can you interpret that signal from another star. And so by looking at something up close like Venus, where we know something about the planet, and the sun, which we know something about because it's up close, we can use that to understand those measurements of other planets better. Because, of course, the thing people really want to find are planets that are like Earth, so that we can be confident that there are other people or things like us, other places in the universe, right? So if we can understand better what the signal would look like if there's a planet like Venus around some other star, then that would be a good thing for in knowing what Kepler's actually seeing.
Yeah, I think the data that they probably got from the Venus transit, once they're able to compare it against their how it matches up against their candidate planets that they've seen so far.
Yeah, that's what they want to do. And 100 years ago they used it to determine the size of the solar system, and nowadays the direct measurements for Venus in and of itself, it's not quite so interesting because we know to within a few hundred meters maybe how far we are from the sun. So it's not quite the same thing. So we used it for calibrating our instruments a little bit too. One of the things that we can't tell exactly is which direction the spacecraft is rolled in space. And so if we're off a little bit to the left or a little bit to the right in terms of our roll, that would show up when we see the Venus image across, because of course we can predict its location very accurately. The other thing that we can't measure usually is scattered light. So we could tell how much energy is moving from one part of our image into another part of our image, and that's really important for understanding sunspots where things are dark all the time. But I love this one because you can kind of see the planet above the surface before it actually crosses, and it's pretty cool. And you can see the sunspots in the background there.
Yeah, the view is really amazing. Compared to a pinhole camera or a reflection through leaves of a tree, or using a pair of binoculars turned backwards. All the methods that we use when you don't have the sophisticated technology to watch.
Well, being in
something
space
like
helps a little bit too. It's expensive to put a camera up there, but it's really worth it because you don't have the atmosphere in the way, and you don't see all these other things happening. In the list of things I sent to you, I think there's one picture that was taken by the New Solar Telescope. Let's see. I don't know if you can bring that one up or not. It was it's number 7 on that little list. I don't know if you can bring it up or not. But the biggest solar telescope, there it is.
From the largest ground-based.
Yeah, so there's a 1.7 meter telescope that's looking at the sun every day, and this was their picture of it, and it's just fascinating. This is just about a second contact, so just after Venus is passed fully onto the disk of the sun, and you can see the effects of Venus's atmosphere there distorting the image behind it. So it's sort of like you're seeing all the sunsets all across the planet at the same time. That little dimple was one of the things that made the measurement that they made in the past so difficult, because it's a real optical effect.
Oh, that's interesting. It's and comparing that telescope to the images that you get from the space-based telescope enables you to really get more accurate measurements.
Yeah. Now what you get with a big telescope is you collect more light. So if you're trying to measure something like the magnetic field, you can do a lot better. And they have actually what they call adaptive optics now, where they move the pieces of the mirror in different ways to account for for the Earth's atmosphere messing up the image. And so you get a really nice image from the ground, but you don't get the continuity. You only get it some of the time. And the nice thing about being in space is it's always clear.
Always. There's never a bad day for weather, right?
Right. Exactly. So this is showing some of the nice things in the atmosphere of the sun. So the surface of the sun is about 6,000 degrees, but the atmosphere above it is a lot hotter. Energy is being deposited by the we think it's by the magnetic field into the atmosphere, and it's heating it up, kind of like a microwave oven heats up the meat, but not the air in between. That energy is being deposited in the atmosphere there, and you see all this activity, and that's above these sunspot regions like the one that you're seeing here, where the magnetic field is complicated and it's moving and it's evolving as it goes across. And what that winds up with is material in the atmosphere that's suspended on these magnetic field lines. And when the magnetic field lines reorient themselves, that material gets ejected into space. And that's one of the things that we worry about for the space weather. So this one is, looking at a sort of intermediate temperature, a few 100,000 degrees. And so you can see the material suspended above. This is looking at even cooler, and you can see those clouds. You can see how they twist, and they're all following the magnetic field. And you can see them untwisting there as the material is released and then falls back to the surface of the sun. And this one is showing two interesting sunspots next to each other.
It's just these visions, these images, these movies of the sun are just beautiful. Seeing the material that being ejected up from the surface, I could just stare at this stuff all day long.
That's one of the perks of the job, is we get to do that. We get to look at those things all the time, and we can finally make those images. Those images that we were just looking at, you can't make from the ground because they're an ultraviolet light that gets blocked by our atmosphere, which is a good thing for skin cancer, but not so good for looking at the sun's atmosphere because the atmosphere is very hot. It's in the millions of degrees range, and regular light doesn't come from something that's that hot. And so you can only see what's happening in the atmosphere above by looking at these ultraviolet wavelengths, extreme ultraviolet wavelengths. What kind of results have you really gotten from the Solar Dynamics Observatory? But since it launched, since it was put in orbit. Well, one of the things that we've realized in a new way is how much everything is connected to everything else. So, for example, if you see an event happening in the northern hemisphere of the sun near one limb, you might see something that happens just a little while later on the east limb of the sun, on the other side of the sun, or in the southern hemisphere. And we've had suspicions that such things are sometimes connected, but now we can actually see how they're connected to each other. Another one of the interesting results that's a little bit tentative at this point is that we can actually see the effects of emerging magnetic fields and sunspots before they appear on the surface with this helioseismology. So it's been one of the things that we've really wanted to do. And there's a hint that if we look below the surface and we look at the sound speed, that we can actually detect a day or two ahead of time that a sunspot's going to emerge. Now, at this point, we can't tell if it's going to be a big one or a small one.
Right.
Although the only ones we've seen are the big ones, because that's where we've looked. But there's at least a chance that we'll be able to see when these things happen. This is one of my favorites right here. You can see this explosion in one place, and you can see the material arcing over the cool material that's suspended. And then when it gets back to the surface, it gets reionized. And you can see that brightness as it comes back down. So this is kind of a failed eruption. It wouldn't be one that would have necessarily a big impact on Earth because it didn't actually escape. But all that material coming back down, and then when it gets close to the surface, it gets brightened again, and you can see it following the magnetic fields again. The intermediate time is when it's not ionized, and so it doesn't really care so much about the magnetic field. It cares mostly about gravity. So this, I think, was an event from about a year ago.
Yeah, so in your notes you had my favorite event on June 7th a year ago. Is this your favorite?
Yeah, that's the one. Yeah, that's my favorite just because it's so spectacular in the different colors. You can see the material going up and coming back down.
I think and the different colors that you're talking about, the different perspectives that we had there. Are those different cameras? Or the
one of the instruments on board is called AIA, the Atmospheric Imaging Assembly, and it has 4 telescopes with, eight filter positions. One of the filter positions moves, so there's a few more. But basically, you can think of it as 8 different colors. All but 2 of them are ultraviolet. And each one of those is sensitive to a different color, and the colors correspond to different temperatures. So one of the temperatures is at sort of 10 to 20,000 degrees. Another one's at 50,000 degrees. And then there's ones at 1 million, 2 million, and 5 million. And so you can see things at different heights in the atmosphere. You can see things that are happening during solar flares. You can see things that are suspended above the active regions. And you can see the cool clouds that connect along neutral lines or places where the magnetic field reverses. And then you can see here where dark things are absorbing that light from behind. And so that's made up of clouds of gas that are really a whole lot cooler. Generally speaking, the bright things are either dense or hot or both. And by looking at all of the different wavelengths, we can actually tell what the temperatures are and what the densities are, which is something we haven't been able to do before.
It's just awesome. As we get to the end of the show here, one of the I guess the popularization tools that SDO has been using. You have a chicken named Camilla, who has been running around planet Earth. She's even been to
sometimes
space.
off the Earth, I guess, right?
Sometimes off the Earth.
She's even gotten rides on balloons. Yeah, Camilla is a lot of fun. We have a good time with Camilla. She's very
so why a chicken? what brought Camilla to SDO and NASA?
You know, Camilla sort of started as an in-joke among some of the astronomers at one of the meetings. Someone brought Camilla in. She wasn't named. We didn't know what her name was yet at that point. And she made an appearance at one of the meetings, and we all kind of got a kick out of it. And then Romeo Dersher, one of the people that I work with, sort of took over for her and sort of, she would show up at various places, and she got to meet an astronaut or two, and then she got to meet a couple more, and then she got a web presence, and, here we are. And I think she just makes it sort of personal. Everybody realizes that it's kind of fun and it's kind of an interesting joke, but she can explain things and do things in a way that's not very threatening to people and makes it very accessible. And that's really a gift.
It is. It is a gift, especially for a chicken.
Yeah. Who would have guessed, huh?
Who would have guessed?
Yeah, she's pretty popular. I think she's more popular than any of the rest of us are, which is good. She's also the most handsome or the most beautiful too. So I guess maybe that goes with it. Yeah,
maybe it's something that we should keep in mind for future for future PR for space or for other sciences. You don't necessarily have to have good-looking scientists like rock stars and sports stars. You can have a chicken.
Yeah, well, I think the thing is you can make a personal connection, and it's not a threatening one. It's very easy, and you can ask what you might otherwise think would be dumb questions, even though none of the questions are really dumb. But there's no barrier to talking with Camilla.
Not much of one at all, except, I don't know, the beak. You don't want to be pecked by a chicken.
Yeah, you don't want to be pecked. That's true.
She's a very nice chicken. She's a very friendly chicken. And if you don't know Camilla, Camilla has a Facebook account. She's also on Google Plus, and she is, and I believe she is Camilla Corona SDO. Is that correct?
Yep, that's right. And she has a very good eye for picking out things that are interesting to look at. So she often finds things happening on the sun before I do. And so I often check my Facebook page just on the way to work to see if Camilla's seen anything interesting overnight, because she gets up early.
Does she, the stuff that she notices, is she noticing images that have been picked out by scientists, or is she looking at the same stuff at the same time? How does it work?
Usually she sees something that somebody else has picked out. There's a group at Lockheed that involved with the AIA instrument, and they go through the data every day looking for interesting events. All of the data are available online, and so you can actually see it yourself within just a few minutes of the time it's observed. So there's no proprietary period, or there's no time when you can't see it, but it's an awful lot of data to look at. And so it really takes somebody sitting down with a good computer and a good computer connection to be able to look at all the data. But people do look at that data every day, and some of the things are automated. You can find some events because they're bright or because they're dark or because we know that they're interesting to look at. But other ones we don't. And Camilla really has her radar out, and she has everybody who's looking at these things knows that Camilla's a good person to let know.
Yeah.
But there are online websites where there's a heliophysics events knowledge base. I think you might be showing it now. And there are a few other websites, too, where you can actually go and look at this data yourself. If you want to be the first one to discover it, you can do it yourself because it's right there. And it's only about 20 minutes behind the time it's actually observed in space. It takes us that long to get the data down and process it and make the images so that you can see it. But it's all there.
That's impressive. And are there any citizen science efforts through the data that you have? Do you have anything organized that people can get involved with?
I don't think that we do. I might not be aware of everything that's going on, but we don't yet at this point. I think there's, that we anyone who can go to this events knowledge base can enter events into the system. And so, it would have to be a little bit more self-started at this point. But, it would be really interesting. I could imagine going back and finding, interesting features and then tracking them through history and having different people identify different ones. We've tried to automate a lot of it just because there's so much data to look at. We're getting 100 megabytes a second from HMI and 100 megabytes a second from AIA. We get, something like 30 images a minute from each of the telescopes. So there's a lot of data being collected, and it's really hard to look at it. And each image is, 8 times as big as an HD TV view. So there's a lot of things to look at. It's almost embarrassing, but on the other hand, you really
embarrassing. We've got so much. It's embarrassing.
You really need to have the continuity of coverage for 2 reasons. One is for the seismology. Gaps are really killers because you have to be able to measure these frequencies extremely accurately. So you have to be able to measure without interruptions for days at a time. And the other thing is, because we don't know where the interesting events on the surface of the sun are going to appear, you want to observe the whole sun all the time, because what happens, it happens on a very short time scale, and you don't have time to retarget your telescope, particularly when it happens, on who knows what time scale, and you don't know when it is. You can't have people looking at it all the time. So you have to the whole thing. And that's really the power of SDO.
Yeah, and like you mentioned earlier in the show, how everything is really connected. You can't just look at one little portion, because there's stuff that's influencing what's happening in that little portion elsewhere on this.
Right. Well, you can see in that picture right there the connections from one part of the disk to the other part of the disk. And the dark areas there are all part of it too. And so when something happens in a bright area, the dark area is affected. And you can see waves traveling when there's a solar flare. You can see waves traveling across the entire hemisphere of the sun. Over a period of a couple hours, and it's just fascinating how all those things happen.
It's just great. Well, are there any plans for the next generation of SDO, or people talking about what's going to come next, or are you pretty happy with what this massive data flood that you're getting currently?
Well, we're 2 years into a 5-year mission, and so it's a good time to start thinking about what the next step is. The real puzzle is that we don't have enough resolution. So we can see the whole sun, and we can see things pretty close, but you can't see things happening on the scale where the physics actually matter. It's sort of like you could see a cloud, but you can't see what's happening inside the cloud, and you really need to know what's happening inside to figure out what's going on. Or you can see the ocean waves, but you can't see the fish underneath, or something like that. So you really need to see something up closer. And so there's a ground-based telescope coming along in about 2018 called ATST. It'll be a 4-meter telescope, so a 12 or 13-foot telescope looking at the sun. And you can imagine the heat problems that we're going to have with that, but it's all designed, and the National Science Foundation is building it. And the other thing is to build a bigger telescope that can go into space so that you can see things with higher resolution, and we're working together with the Japanese to do that. The other thing is, which parts of the sun can we not see? We can't see the poles of the sun because we're close to the equator, and it's really hard to see what's happening up there. And we can't see the other side of the sun. So sending something around to the other side of the sun so that we get a little more advanced warning for what's coming around are the other things. And there's another mission called Solar Probe, which is being built, which is to go close to the sun within 10 solar radii, so it gets very close to the sun, and we can actually sample what's happening there and see if our theories and our models for what's happening are actually true. And that'll be about 2017, 18, 19, 20, depending upon how long it takes to get there.
Well, I'm excited, and I look forward to hearing all about it, because the sun, it's the biggest, probably most important thing in our solar system.
Certainly the heaviest. You might ask your spouse about what's most important, but
yeah.
Or your
it's all perspective, I guess.
It's certainly the most important astronomical body other than the Earth for us.
Yeah, absolutely. And it's just wonderful that people like you are studying the sun, and that I just thank you so much for coming to talk with me today about everything that you're learning. It's
Enjoyed it.
And there are a few websites that you've got where people can find stuff. You mentioned the Solar Dynamics Observatory website. Are there any other websites that would be really important for people to find out more information about the sun?
Well, we've got a sort of a public education website called solar-center.org. solar.stanford.edu. And we've collected a lot of material there that's suitable for people who aren't necessarily solar physicists. And you can see something about the history of the sun, history of people's observations of the sun. And then some of the other sites, if you just type in SDO on Google or you type in fantastic event, you'll pretty much be taken to it.
Fantastic.
Yeah.
Once again, thank you very much. I know you have some celebrations to get to, so I will not keep you any longer. Really appreciate your time today. This was very, very informative, enlightening interview.
Oh, good. I hope it was as fun for you as it was for me. I enjoyed it too. So good talking to you. Nice show. Really enjoy it.
Thank you. I had a lot of fun, and have a wonderful evening, everybody.
Thank you.
Todd Hoeksema from Stanford University, the Solar Observatory Group, and NASA's Solar Dynamics Observatory. And you can find more out about the sun at all the great websites that he recommended. And this is it. It's the end of Dr. Kiki's Science Hour. I am Dr. Kiki, and until next week, well, actually not next week. I'm on vacation next week. I'm going to be on a beach somewhere soaking up some of the sun that has reached our planet. And until I come back 2 weeks from now, you can find my science-y pursuits on social media, Twitter, Facebook. I'm Dr. Kiki. Google+. I am Kiki Sanford. You can subscribe to Dr. Kiki's Science Hour in iTunes, and you can find past episodes at twit.tv/Kiki. Also, if you need any more science-y goodness, there is This Week in Science, which is ongoing. It broadcasts live every Thursday night at twit.tv. If you can find past episodes of that at twist.org. So I'll be back in a couple of weeks. I hope that the world is nice and sunny for you. Thanks for tuning into my Science Hour. And remember, all I really ask is 1 hour a week. And I hope that this hour made your world a whole lot more interesting. Now for your science meditation of the week.
Having Ray Bradbury here was incredible because, in particular for Mars, he really has been one of the voices from very, very early on for going to Mars and exploring Mars long before we knew how to do it. He was taking us there in our minds.
Let me introduce you to some of the other people who drive the rover with me.
Yes, sir. So our rovers look just like this.
When he came to the operations room and we showed him the model of the rover and the large-scale panoramic pictures that we've taken, the actual photographs of the surface of the planet, it was like watching him experience it as a child almost would experience it, just the wonderment. He has never lost that wonder for Mars that he's always conveyed in his books.
There you go. You're getting the hang of it already. We're going to have to hire you.
Showing him how we control the rover and using the simulator and letting him basically drive the simulated rover across the surface of the planet and letting him see the reality of that was very rewarding for us because we could tell how much it meant to him to see this that once that was only fiction, that partly because of his vision and his sharing that vision with us, that it's now become a reality and that we're actually there.